Hello and welcome everyone to iBwave's Deep Dive webinar, where we'll dive into a stadium's wireless network design. I'd like to welcome you once again. My name is Amna and I work in marketing and communications at iBwave. We're very excited to be with you today presenting our latest Deep Dive webinar, where we take our advanced research findings and apply them to real-life cases and venues to deliver practical and technical indoor wireless knowledge that you can apply. Our speaker today is Vladan Jivromovic, our research director here at iBwave. Vladan has 20 years of professional experience in the wireless telecommunication industry and 13 years of direct in-building experience. At iBwave, he is the principal architect of RF propagation and optimization algorithms applied to our in-building design and planning tools, and he also develops technical courses offered through the iBwave certification program. Vladan holds a PhD from University of Colorado at Boulder. In just a few minutes, Vladan will go into the technical details of the challenges and best practices of designing wireless networks for stadiums. But before we begin, I just have a few housekeeping items to mention. First of all, thank you for all the questions you sent while registering for the webinar. If you have additional questions, please type them into the questions box on the GoToWebinar control panel at any time. We will answer as many as we can during the last 15 minutes of the session and will respond to the remaining ones after the webinar. For those who may have audio difficulties, we will try to speak as loudly and clearly as possible, but please make sure to check your audio settings on your computer or phone as you dial in. We will be recording today's webinar and sending the recording as well as the slide deck and white paper to everyone shortly. The recording and the white paper will also be available on our website in the next few days. For those of you who are unfamiliar with iBwave, iBwave is a global provider of innovative in-building wireless software solutions to help operators, system integrators, and equipment manufacturers better design and plan multi-technology wireless networks inside buildings and venues. You can learn more about our software suite and our in-building training on our website, iBwave.com. Now, without further ado, I'll pass the mic over to Vladan, who will get into today's topic.
Thank you, Anna, for your kind introduction. Hello, everybody. Good afternoon. This is our next installment of Deep Dive webinar series. We are going to be talking about wireless networks at stadiums. The agenda is very full today. We're going to start by talking about stadiums around the world and why stadiums are attractive for dedicated wireless networks. We'll talk about general design requirements for stadiums. We will talk about areas that are targeted for coverage, both inside the stadium but also outside the stadium. We will talk about best practices. And this is going to be a majority, obviously, of our presentation. When talking about best practices, we'll talk about survey, site survey, RF survey, CW measurements. We will talk about 3D modeling, why we want to spend hours, not minutes, modeling these venues, and how detailed modeling actually pays off in the long run when it comes to analysis, propagation analysis, but also other stuff that is involved in designing and deploying the networks. We'll talk about handoff management, where we want our subscribers to hand off to and from the macro network and into the dedicated stadium network, and but also about locations where we do not want to see a handoff occur. We will talk about macro coverage, what happens when it seeps into the stadium, and why it is not good for performance of dedicated stadium network, and how to manage macro coverage. We will talk about sectorization, why we need it, and what kind of antennas we actually prefer for sectorization. We will talk about passive intermodulation, which we covered in more details when we talked about in-building networks in general. And then most of my best practices talk will focus on capacity dimensioning. I spent earlier today in EMEA presentation close to 20 minutes talking about that, and I expect that I will spend about as much time today. It's very detailed. Then we're going to briefly touch upon possible solutions for dedicated stadium wireless network. We will give examples of 3D RF coverage maps, and then we will summarize what we have learned today, and then we will leave about 5 to 10 minutes for Q&A. Now, stadiums around the world. When we look into the stadiums that have more than 30,000 seats, and those are the stadiums that are of primary interest for dedicated stadium networks, they're mostly located in North America, Europe, and APAC region. There are almost 1,000 of them, and of those 1,000, of special interest are the ones that are over 50,000 seats. And so you see they are about, let's say, 45% of that 1,000. Those are the stadiums that you will get the easiest return of investment because they have the most spectators, but they are also the most complex to design. And we will give examples of top 3 stadiums in the world. Number 3 is University of Michigan in Ann Arbor that seats almost 110,000 people. And if you look at that stadium, you will notice that aside from one structure, when the TV commentators are and the VIP section, really you have only general seating. It is really not a very modern stadium, which typically has one level, which is called club level, that has suites with VIP personnel in there. So this is, I would say, old school type of stadium. It's large, but it does not have, many difficult spots to cover at the seating wall. It does not have VIP areas. The second place belongs to a stadium in Kolkata, India, and it is pretty much the same way, just the general seating with that VIP section in the middle for TV and broadcast, and probably a few others. And finally, there is the biggest stadium in the world is in North Korea, 150,000 spectators, and we can't really see how it looks like from on the inside, which I guess was the whole point of this picture, to show that this exists, and we can't see how it looks like. But my assumption is it's probably general seating with a VIP area. So now let's move on to design requirements. Typically, what you want to have in a stadium are all technologies present in a local market. So what do we typically see? Well, we see those worldwide technologies such as GSM, UMTS, and LTE, 3GPP technologies. We also see Wi-Fi deployed in hotspots, and then we also see public safety. Now, as for public safety, there is not a single technology associated with it. There are various ones depending on the part of the world, and also but it is also listed there because it is almost always a requirement to include that in the dedicated network at the stadium. Then we have local technologies, for example, CDMA 2000 and EVDO. They are found in North America and parts of South America and Southeast Asia, but in Europe and also Africa. And PHS and AXGP, which are deployed in Southeast Asia, but not anywhere else. As for the coverage requirements, the minimum signal is listed here for GSM and UMTS. It's neg 85 dBm. For LTE, it's neg 95, and for 802.11, it's neg 75. However, these are minimum signal requirements when the residual macro signal is low. When it is significant, then alternative definition is, which is to say we have to have IBS signal at least 5 to 7 dB stronger than the residual macro. The reason for that is we want to provide the dominance of in-building signal at the venue. We want to dominate macro signal. So, in other words, those are general requirements that you will see typically in dedicated stadium networks. Now, as for the coverage requirements, what we see inside the stadium, obviously, is seating bowl. The seats have to be covered, but there is much more than that. For example, I mentioned VIP boxes, and those are also called corporate boxes, and they are usually found in a separate level or called club level. And also TV commentators area are usually nearby. So they have to be covered. They're not typically not open. Usually there is a glass that separates that from the general seating area. And then underneath the bowl, what we have is food and drink concessions and shopping area. Usually they are located near the entrances because that's the first thing that spectators do, go in and either buy a souvenir or get food and or drink. What we have deeper down in the bowls of the stadium, in the ground level, we have press rooms and dressing rooms for the two teams that are playing, and for the press conferences before and after the game. Also, there is a possibility that the conference room exists throughout the stadium. They have to be covered as well. So those are all hotspots that require the coverage at the stadium. Outside of the stadium, what we have is areas where people tend to congregate before and after the game, which is to say that any and all train stations and subway stations, metro stations that are nearby the stadium have to be included as a part of the stadium network. Roads and tunnels near the stadium also have to be included, and so does car parking lots. And if there is a separate tailgate area, that obviously needs to be included as well. So pretty much all the areas where spectators tend to linger before and after the game. And this is especially of interest in North America, where tailgating is a prevailing phenomena at college football games and the professional football games. So we have to take into account that this going to the game in Northern America is more of a half-day experience as opposed to maybe a 2-hour experience if you view that from a viewpoint of let's say European soccer game. Now, as for the best practices, we start with site survey. Site survey is basically what you need to do when you first visit the site. Examine potential locations for head-end equipment and potential locations for maybe remote units and possible cable pathways, and also you need to identify mounting places for your antennas. And all that should be located on a plan, preferably in digital form, so it can be then corrected and maybe uploaded in the cloud and shared with other engineers. But aside from that, RF survey should be performed because we said that there may be a residual macro signal at the venue, and we need to know how strong that signal is. So taking the detailed RF macro survey throughout the bowl area and also underneath it in the shopping area and also in the VIP boxes and also in the press and dressing rooms is a must. Now, lastly, CW test data should be taken. If we identified possible locations, we should try to put an antenna there and inject CW signal in there and then take CW coverage data, which then will be used to calibrate propagation model in a software tool of your choice. If we cannot put antenna in the exact location, then bring a tripod and try to place as close to the location where it's going to be and as high as that location is. So those are the best practices for survey, RF survey, CW test, and site survey. As for 3D modeling, what we need to recognize is that stadium is not only a multi-level, but also a very heterogeneous RF environment. What it means is that the seating area, we have inclined surface and line of sight. In retail area underneath, what we have is a horizontal service and combination of line of sight, non-line of sight, and diffraction. So this is best analyzed if you build a 3D model of it, and then allow the propagation to take into account all those different RF environments, because interfering signal will be coming from all levels and directions. But also, the detailed 3D model is going to help quite a bit in getting an accurate bill of materials, because you are going to be dealing with cable length estimates. And the closer you can get through the real value, the better off you will be in the long run. But making a complex 3D model such as this can take up to 20 hours. It can take quite a bit to actually do detailed modeling that is necessary for large stadiums. Now, moving on to handoff management. What we want and what we don't want for macro to IBS handoff. What we most definitely don't want is to have a handoff present in the seating area or any place else at the stadium for that matter, because what's going to happen is we're going to have a lot of ping-pong effects inside the stadium, which will worsen the network performance. Now, whether we are going to hand off at the stadium entrance or at the high traffic areas outside the stadium, which I pointed out in a slide before, is really a matter of observing the pattern of spectators before and after the game. As I have mentioned, in North America, they tend to linger before and after the game quite a bit. In that case, you really would want to move the handoff area away from those places where they tend to linger, meaning don't let them hand off at the tailgate area or a car parking lot area. Try to get the handoff further away from there. If it is more of a European-style soccer fan behavior, when they get in and get out of the stadium rather quickly, then the handoff can be at the stadium entrance. Now, as for the macro coverage management, historically what would have happened is that, operators early recognized that there is a lots of revenue to be had at stadiums, but at the beginning it was voice only, really. And then so what they were doing is they would say, okay, I'm going to build a cell site nearby, and I'm going to point a sector towards the stadium, and that's what's going to give me good coverage, voice coverage inside the stadium. Well, that worked quite well for a while, but now it's more about capacity, and yet we still have a very strong signal, may have a very strong signal from that sector that was pointed down toward the stadium back in 1999. Now, when that happens, then this is what you get at the picture on the right. There is an area with the hot RF signal, macro signal, which is shown in yellow. And then a part of the stadium is in darker color, which basically means the signal is not so hot from that sector. So what to do? Well, the easiest way is to down tilt that sector. It's going to reduce the coverage of that sector, and it's going to direct the RF rays to go through more of a concrete, and that will basically reduce the signal level, macro signal level at the stadium. So that's a technique to help with the macro coverage. But what about inside the stadium? This is a densely populated venue, and what we obviously cannot cover the whole stadium with one sector. So we need to split that into smaller areas in order to be able, and each of those smaller areas should be a separate sector, and that's how we actually handle capacity. So this is an example that I showed that has a stadium of with 24 sectors. Basically, each sector serves 2,000 to 3,000 subscribers. And then it is not unusual to see such large number of sectors in a stadium. This was an assumption that was covered later on in a capacity example. And this is a stadium that has 60,000 seats, 24 sectors. We have seen stadiums with more than that, so this is not unusual. Now, what we need to make sure is that the overlap between those sectors is minimal. And for that, we have to use antennas that have a very narrow beam width. As an illustration, I have given here 3 antenna patterns, and they are grouped in pairs. The upper one is horizontal, and the lower one is vertical. So the first one is 60-60. The second one is horizontal 30 and vertical 60, and the last one is horizontal 30 and vertical 30 as well. These are the types of antennas with those narrow beams that you would want to use to isolate those sectors and to minimize the sector overlap. Then moving on, we talk about passive intermodulation. It is generated in neutral host networks when we have 2 or more signals that belong to different frequency bands. And these 2, when they mix, they generate the products called PIM. And those PIMs have a lower amplitude than the original signal, but wider bandwidth, as we see illustrated on this picture. Where is it generated? In passive devices, in cables and connectors, but also at rusty bolts near antenna. Rusty bolt is oxidized bolt, and that tends to affect the antenna pattern quite a bit. So how do we avoid PIM? Well, first of all, we should not use braided coax cables and end connectors because they are known sources of PIM. Instead, silver-plated 716 DIN should be used instead. Avoid placing antennas near metallic objects, including rusty bolts, and do not use equipment with unspecified PIM ratings. And prior to antenna installation, on-site PIM testing should be used using antenna on a pole. This was covered in more detail in one of our previous deep dive webinars. And now finally, we go to capacity dimensioning. Here, what we're going to do is we're going to talk about how do we define a typical calling pattern for users in a stadium. What are the assumptions that we may assume regarding their calling pattern, and what are the preferred data sessions that they will have at a stadium. And then based on that, we are also going to make some assumption, and that is to say that if the network is congested, if the application for some reason cannot be used, then we will treat that as a denied service, and we will calculate call denial, or what we call blocking, based on the user profile and the number of subscribers. Before I go on, I just want to point something out, that we use the term call blocking and call denial, even though we are fully aware that this is a data session, and data sessions really do not have a denial of service like voice circuits. Instead, they have excessive delay. And when excessive delay happens, what happens is that the customer perceives the network as slow, and they usually just abandon the application. They basically decide to either kill the window or just put the phone in their pocket and not try to use it again. From the practical standpoint, it really is that those calls that were too slow, they really are treated as a block, as the ones that never really went through from the point of the user experience. So we will, when we talk about call denial or call blocking, that's the percentage of attempted data sessions that had excessive delay and were therefore abandoned by the subscribers. So when defining a user profile, what we need to assess is what is the service type that will be used, what's the duration of each connection, and what is the data rate. At the stadium, what we are going to assume is that not many people will be using video conferencing due to the crowd noise, the audience noise. When I say that it is going to be 5 millierlings per user, it doesn't mean that every single user is going to try to use it once in an hour for 7 seconds and then abandon it. It just means that when you average out all those connections made in a stadium, it turns out to be 5 millierlings per user. As for video streaming, most stadiums ban video streaming outright. I have still made assigned 1 millierling per user, not because I'm thinking that they're going to try to use it for 2 seconds and then abandon it, but rather there are those savvy customers that know how to circumvent this ban, and then when it all averages out is that we still have some video streaming activity in the stadium. Also, we're going to make an assumption in this analysis that LTE voice over IP has not been applied in this network. All calls are on R99 WCDMA. By the way, the analysis for this will be analysis for LTE only. I have HSPA and R99 analysis in that white paper that will be sent out after this webinar. So now that we have that, we just to make sure that we move on forward, just to address a comment as to for the duration of sessions for email, browsing, and data download. Basically, those three are the ones that generate the most activity in the stadium because they really do not require audio for it, and still are not as the data rate is not required. Data rate is not as high, so they are allowed to be accessed throughout the stadium. And most of the traffic goes to those three. So the next step is to figure out how many subscribers are we dealing with. So this is a stadium of 60,000 seats, and I have assumed that there are 3 wireless service providers. And I have their penetration rates, and this is general knowledge. And I also had to make some assumption about the breakdown of their subscribers between 2 technologies, UMTS and LTE. I have assumed, for simplicity reasons, that GSM or CDMA, 2-generation CDMA, are not in the network. So only UMTS and LTE. When we break this down, we see that I have 18,000 LTE subscribers for wireless service provider A, and it has only also 6,000 UMTS subscribers. And I have the number of subscribers for B and C. I'm only going to focus on LTE and those 18,000 subscribers going forward. By the way, if you look into the penetration rate for those 3, you will see that it does not add up to 100%. Assumption was made that the 4th wireless service provider decided not to be present at the stadium. So that's why we have only 70% of the general population. Our next step is to establish a link between spectral efficiency and SANR. We have to have that because SANR coverage map is going to be critical when for capacity calculation. We will show later on why. But first of all, the table to the right is taken from 3GPP document, and it gives the relationship between CQI, modulation, and spectral efficiency. What we don't have is the relationship between SANR and CQI, which is not specified by 3GPP, and it can be obtained directly from vendors or from scientific papers. What you see on the left-hand side, this table on the left, CQI versus SNR, was taken from a scientific paper, and the reference is given in the white paper that we will be distributing shortly. When we combine those two, what we have is a table on the right, which shows you relationship between CQI, modulation, and spectral efficiency and SANR. It is a busy table. It has 15 entries. Because I'm going to be showing examples of capacity calculation, I simplified that to a table with 4 entries without losing general principles of calculation. So instead of a big table with 15 entries, we're going to be dealing with this smaller table that has SANR 3 dB and higher. So the next step is for LT to figure out how many physical resource blocks are needed to support those listed service types: email browsing, video conferencing, data download, video streaming throughout the stadium. We know what the required data rate is for each, and one of them, we now have to figure out how many physical resource blocks we need for each of those applications. First of all, we have 4 different SANR ranges, and each of those ranges has different spectral efficiency. It means that I'm going to have a different number of PRBs needed to support those service types that are listed. So, for example, in range 4, when SANR is greater than 20, my MCS efficiency is 5.55. PRB data rate is MCS efficiency times number of PDSCH resources divided by duration of PRB transmission, which is 1 millisecond, which is also 1 subframe. 1 PRB has a total of 168 REs. Not all of them are PDSCH REs. So when we take overhead into account, then my PRB data rate for SANR of 20 and higher is about 900 kilobits per second. Now, when you look into service types listed, email browsing and video conferences are all less than 900 kilobits per second. So all of them need just 1 PRB. Data download is just over that number. It is 1 megabit per second. So if my PRB, 1 PRB is about 900 kilobits per second, I have to assign it 2 PRBs. Why? Because a PRB is the smallest addressable unit. I cannot assign 1.5 PRB. I have to give integer numbers. So data download, I need 2, and video streaming, because it's 2 megabits per second, I need 3. So as you see, those data packets needed to transport those different service types are of a different length or a different size. It can be as small as a single PRB, can be as large as 12 PRBs if this is video streaming in range 1, where SANR is between 3 and 9. So in range 1, you will notice we have packets of a greater size than in range 4. And that is to be expected because range 4 has a great SANR, and range 1, well, not so good. So this is going to be, repeat as a theme later on in calculating call blocking. First, before we go there, we have to figure out how many sectors do we really need for those 18,000 LT customers. And here I have given you a detailed calculation where I made a few, I would say, reasonable assumptions to get to where I wanted to get to, which is the number of sectors. First of all, we have to start with the maximum achievable data rate coverage map. And those data rates are for a 10 megahertz LT 2x2 MIMO. And they are calculated directly from using those MCS efficiency values in the previous table. Because I had a SANR table that has 4 entries, I'm going to have maximum achievable data rate map that also has 4 ranges. And I have to make some assumption regarding the percentage of the coverage for each range. And those assumptions are reasonable if we expect high density of sectors in a venue, which is to say very high data rate of 58.3 megabits per second. It can only be around or near the antenna, which is shown as 20% coverage. Likewise, in the area where sectors overlap, I will have lower data rate quite a bit, which corresponds to 8.8 megabits per second, and I assume 30% coverage is there, 30% of the overall coverage is there. Once we have those assumptions nailed down, then it's easy to calculate average data rate per sector. That's a requirement. That's actually not a requirement. This is average data rate per sector. This is what we are assuming that we will see after we have a dense sectorization in the stadium. Next step is to look into the service types. We have already defined connection duration. We have defined data rates. What we are missing is desired call blocking or rejection, call rejection, or how many percentage of the connection request that gets delayed beyond the specification. So I have put down some numbers, 3, 4%, 8%, 10%, 20%, and the question is, how did I come up with those numbers? Well, those are the numbers that you typically see in those stadiums if you are targeting your overall call blocking, meaning for all the services in the stadium to be between 5 and 10%. Also, you do expect to see lower call blocking for applications that have lower data rate. So it is natural that your email that is only 100 kilobits per second is going to have much lower call blocking than your data connection, video streaming, which is here 10% and 20% respectively. So once you have those assumptions there, then what is left is for us to figure out two things. First of all, what is a duty cycle that we should be aiming for? Here I have assumed 40%. Typically in networks you may assume anything between 40 and 60%. Duty cycle is really the same as cell load, and basically is measure of utilization of your resources in the network. So if you have 50% cell load, that means that on average during busy hour, half of your resources are in use. Well, why not 100%? If you think about it, if you have 100% utilization all the time, what it really means is that nobody can get on your network. It also means that you have 100% call blocking rate. Nobody can get in because your network is full all the time. So 40% is a decent number. And then finally, this is a salient assumption that we have alluded to previously, and that is to say that each subscriber that is in data session, in data connection, is served once and only once during the 10 millisecond frame. And because 10 milliseconds frame are broken down into subframes, and each subframe has 1 millisecond transmission duration. So what we are saying is that in 1 millisecond subframe, I will address my user. It can be multiple users, but I will say I will address a user. And then in the next 9 subframes, I won't address that user again. He will have to wait for the next frame. So in the next frame, I'm going to serve him in the first subframe, but that really means that I have a 10 millisecond gap between consecutive transmissions to the same user. That needs to be taken into account when we calculate required data throughput. And finally, I have, after I define all that, I'm able to calculate total data throughput in the stadium, which is 692 megabits per second, and when I divide that by 29.1, I get, and I round it up, I get 24 sectors. So this is what you get. There is a little bit of assumptions here that I believe are reasonable, and then it's a good starting point for you figuring out how many sectors you're going to have in the network. But why do I need to know in advance? Well, you need to know because you really need to figure out the offered traffic in the stadium. And for offered traffic, you need to know the number of subscribers. When I say number of subscribers, I mean really number of subscribers per sector, because you will be calculating your call blocking for each sector. Why? Well, you need to know if your sector is performing well or not performing well in the networks, And in a stadium, we don't expect all 24 sectors or whatever it may be to have, all the same capacity statistics. So that's why we want to know the number of LT subscribers per sector. So once we know that, then we look into SANR distribution. Each of those ranges has certain coverage percentage, and assumption is that we have uniform distribution of subscribers per sector. So if range number 4, which is where SANR is really good, is only 20% of the coverage, then of my 750 subscribers, 20% of those go into range number 4. And likewise for range 1 to 3. Once I have that, I can multiply the number of subscribers in each of those ranges with the call duration to get traffic in Erlang. This is my offered traffic in a stadium for each range, for each application. And when I sum it up, I see that my total offered traffic is 229.5 Erlangs. Finally, we get to the formula that we use to calculate call blockage, or percentage of the of unsuccessful attempts, or unsuccessful connections, or connections that are overly delayed. The formula that we use comes from ITU R recommendation, and the reference is given here. Now, one thing that I want to point out, I mentioned here 500 PRBs in 10 megahertz channel. And I always get the same question, well, no, it's 50. Yeah, you're right, it is 50. The 10 megahertz channel can only have 50 PRBs, that is true. But be mindful that we have just said that the frame is 10 milliseconds, and the subframe is 1 millisecond, and I have transmissions in each subframe. In each subframe, I can address a separate set of LT subscribers. So if all of my customers are using email or web browsing, I can each give them only one PRB, and in theory, I can serve 50 customers, 50 subscribers in the first subframe, then 50 different subscribers in the second, and 50 different subscribers in the third, and so on and so forth. So I can serve 500 different subscribers in one LT frame. And then, because I assumed that each of them will be addressed only once in each LT frame, I can address those same 500 subscribers in the second LT frame, and so on and so forth. So you see that I can go up to 500 unique LT subscribers, and each of them will have their own PRB in a frame. So that's why I say 500 PRBs. It is 500 unique PRBs in a frame when I have 10 megahertz RF channel. So those are the starting assumptions. I also have 5 different data sessions, and I apply this formula here. What you see row is traffic in Erlangs, which we offer traffic that we calculated. New M is number of PRBs needed for each service, which is from the table that you are just seeing. And then we also have the total number of trunks, which is 500 PRBs that we are using to calculate this. When we apply the formula, we get this table which gives us the call rejection for each service type in each range. Once again, this is not a true rejection because this is data. This is just a connection that is delayed more than 10 milliseconds, and thus it has degraded. The perception is the network is slow and the customer drops the session, does not want to continue. I have made some assumptions earlier. I said 3% for email. If you look into what we have from range 1 to 4, we really have close to 3. I have said 4% for browsing. When you average out those numbers, it will come close to 4%. I have said 20% for video streaming. When you average out from all the ranges, it will get close to 20%. But more to the point is, if you look at those calls that were rejected, you will notice that the area where SANR is really good, we had a much lower percentage of rejection than in area when SANR is not very good, which is range 1. And that leads to the conclusion that a service with higher data rate requires more PRBs or larger packets and has greater blocking percentage, which is a general conclusion which will be applied regardless of the venue. This is just the way it is. Finally, we get to the key data. Carry data traffic is one of them, and that is the traffic that successfully went through the network. And that carry data traffic is calculated as offered traffic times 1 minus blocking percentage. And we had offered traffic table in a couple of slides prior. We had blocking percentage table in the previous slide. So from those two, we calculate carry the data. Offered data was 229.5 Erlangs. Carry traffic is 212.5. The difference between those two is about 17 Erlangs. When you divide that by 229.5, you will get what we call composite call blocking, which is about 7.4%. And as I have promised, the target was to have this number between 5 and 10%. Data usage, I won't go through the details of that. Now, duty cycle is something that I would like to bring your attention to. We said we are shooting for 40%. We got 49.5. How do I know it's 49.5? Well, I told you I can serve up to 500 different subscribers in an LTE frame. Imagine that those 500 PRBs are busy all the time during busy hour. They will generate 500 Erlangs. My carry traffic is 212.5 Erlangs. When I divide those two, I get 0.425, which is 42.5%. That is my duty cycle. IVS solution, there are really small cells are in play, as is neutral host DAS. But typically what IT managers don't like to do is to put multiple antennas in the same location. Also, carriers don't really like to share small cells. And because of that reason, we really have not heard of small cells being deployed inside the stadium yet. And that's why we say neutral host DAS system is really something that is most likely to be deployed. Passive or active doesn't matter, but this is something that needs to carry the signals of multiple operators. And finally, I'm giving you illustration of some nice 3D snapshots. LTE, this is RSRP. The next one is SANR. As promised, you see that it looks very heterogeneous. You see a lot of yellow and blue and green. And that's because, as I said, when you have high density sectorization, you really can only expect a really good SANR to be very close to the antenna. And SANR gets degraded rather quickly at the cell edges, which is what you see here. When you move on to LTE, likewise, you see a very heterogeneous looking map for the same reason. I mean, SANR and MADR, maximum achievable data rate, are closely interlinked, and that's why the percentage of one corresponds to the percentage of the other. Finally, we go to the summary. What have we learned today? Well, we covered quite a bit of ground. We talked about stadiums around the world, design requirements for those stadiums, target areas for coverage inside and outside the stadium. Talked about best practices, talked about survey, site survey, RF survey, CW measurements. Talked about 3D modeling, handoff management, macro coverage management, sectorization, passive intermodulation, and finally, capacity dimensioning. I have mentioned briefly possible IBS solutions. I have shown you a glimpse of RF coverage maps, and now it's time for Q&A.
Thank you, Glenn. Now we will get to some of the many questions that everyone put in during registration and right now via the GoToWebinar box. So the first question I have is, how do we calculate the number of sectors based on user profile, number of users, and simulation for maximum achievable data rate coverage map?
Okay, well, this was the question that we have received prior to the webinar, and I was just going to point out that this is the critical table for that. There is quite a bit of assumptions that we have made to get this, but I believe those are reasonable assumptions for a densely sectorized venue, such as a stadium, and that from there I have even given you formulas that you can go and take a look. One of the questions that I get, I wouldn't say all the time, but the question is, how many concurrent email sessions can you have in a stadium? And in this formula, it kind of points this out. First of all, we start with the total number of LT subscribers, which is 18,000. Then we multiply that by the probability that each subscriber will be in email session. And that probability is tied to connection duration. So connection duration in millierlengths and probability of being in a call are interlinked. So once you multiply those two numbers, you have the number of subscribers that are in concurrent email sessions at the same time, if you don't take into account blocking. But if you want to take into account blocking, then you multiply with the third term, and then you finally get the total number of people that are using email at any given time in a stadium. And that's what you can get for all other applications as well. Once you have the total number of people attempting to use email and all others, you multiply that with the data rate, and this is given in megabits per second for each of those applications. And then you have to take into account the duty cycle, which is for 40% here. As I said before, if you don't take into account duty cycle, then you are implicitly assuming that it is 100%. And you really cannot use the network that has duty cycle of 100% because that means that nobody can get on the network. And finally, you have to take into account that you have a pause in data transmission for each user, which is natural because you don't really transmit continuously for one subscriber. You transmit within 1 millisecond and then you take a break and then address that customer later on as well. This is just the nature of data network. So anyway, this is the key for figuring out how many sectors you're going to need for a given number of subscribers for given applications and desired call blocking.
The next question we have, how do you model the difference between full and empty stadiums? How to model body loss?
Right. So keep in mind one thing. Yes, there is body loss, obviously. And in our tool, we can put a layer there, and the layer of, let's say, I think we have lard or something like that, which basically, okay, not all of us are all lard all the time, but it's close enough, you know, for modeling the human body. But what is more important is keep in mind that when you have an empty stadium, your cell load is equal to 0 or 1%. So when you analyze propagation of an empty stadium in our tool, you have to set cell load to something like 1%. And that is going to mimic what's happening in the stadium if you are doing the RF survey of a deployed IBS system without anybody in the stadium. Then what happens when there are people in the stadium, then your cell load is going to go up to 50%, 60%, or what have you, and you have to change that in our tool to set the cell load to that value, and that's going to give you the more accurate behavior of SANR when there are people in the stadium. So you have to do both. You have to put a layer of lard, and then you have to also make sure that your cell load is set to 50 or 60%. That's why you basically have MADR that is lower than what you expect, and in your SANR it is lower than what you measure. It's because cell load was not set properly.
Thank you. The next question is, how do you design for both? Number one, coverage in the bowl for sports events. Number two, coverage on the field only for concert events. How do you provide RF coverage on the field without increasing SINR in the bowl?
Right. So what's happening there is that basically the people move. Okay. The distribution of people is not the same in those two cases. So what you have in a stadium, obviously, you have people sitting in the bowls. All of them are full, and there are people on the field. And those people on the field, obviously, they're playing the game. They're not making calls. So you don't really care about SANR that's on the field. You really do care for SANR on the ball. Now, what's happening at the concerts, about a quarter of the stadium is empty, and that's the seats that are behind the stage. So you really don't need those sectors. What you instead need is those sectors to somehow be transferred to cover the field. Well, first of all, what I think what you would need is for stadiums that have cover, that they usually have a catwalk, which is above the field. There you would put antennas that are to cover the field area, but you don't really need them to transmit anything if there is a football game. For a concert, though, you would need them to transmit, and you don't need those sectors that are in MPCs to transmit. Now this is the job for self-optimizing networks, or SON. They are actually should be able to help there, because in SON networks you can actually tell particular eNodeBs that you want them to transmit in a certain time frame, and then reduce the power or not transmit at all at a different time frame. So you can actually program that into the network, how you want those transmission pattern or changed. You can even program down tilting of the antennas in real time, for a particular time of the day. So basically a combination of installation of antennas and a catwalk above the pitch or the field, and the SON network may be able to solve this problem. Now, as to how do we do this in stadiums that are open air, I'm not quite sure about that. So that's something that is an open question for me. What should you use for fade margin in our tool? That's a good question. I know we have given some numbers there about 1, 2, or 3 dB. I'm not quite sure, but just you can use a default value there if you wish to. In capacity dimensioning spreadsheet, you mentioned that the question was, you mentioned that you use subscriber once a frame, and the question is, does it mean that eNodeB scheduler has to be set to round robin rather than normal proportional fair schedule? Yes, you're right. This was an example of a round robin assignment in a scheduler. We'll have to assume something, and this is just something that we decided to implement it that way in our tool and in our example. And we currently have it deployed that way in our tool, and if we hear more requests for a different scheduler, then we may take that into account.
Thank you, Lenin. We're out of time. I would like to thank everyone who joined us and for all your questions. To continue the conversation, I will encourage you to join our LinkedIn group, the iBwave in-building community. If you're not a member yet, I encourage you to join us. You can look for a recording and a slide deck from today's presentation in your inbox in the next few days. The white paper that was used to develop this webinar will also be available on our website shortly. Thank you again, and I wish you a good day. I will now disconnect the call.